Good morning, students. Our next theorem is to find the dimension of the algebraic dual space of a finite dimensional vector space. We will show that the dimension of a finite dimensional vector space is same as the dimension of its algebraic dual space. So the theorem is, let X be any n-dimensional vector space and E the set consisting of the vectors e1, e2, e3 up to en. This is a basis for the vector space X. Then we are to prove that the set F consisting of the functionals f1, f2, f3 up to fn given by fk of ej is equal to del jk, where del jk denotes the Kronecker delta function. If j and k are different, this takes value 0. If j and k are same, this takes value 1. We are to prove that this set F is a basis for the algebraic dual x star of the vector space X, and also we prove that the dimension of algebraic dual of X is same as the dimension of X. Now, in order to prove that this is the basis for the algebraic dual of X, we will have to prove the two conditions for basis. Firstly, we show that this set is linearly independent, and secondly, we show that every element of X star can be written as a linear combination of elements of F in a unique way. So firstly, to prove this set is linearly independent. To prove linearly independent, let us take scalars beta 1, beta 2, beta 3 up to beta n such that the linear combination beta 1 f1 plus beta 2 f2 and so on up to beta n fn is equal to 0. We prove that in this linear combination all the scalars beta k are 0. It means we are to show that beta 1, beta 2, beta 3 up to beta n all the scalars are 0. Now from here, because summation beta k fk that is 0, it means the image of every element of X under this function that is 0. So we can say that summation beta k fk x is equal to 0. Now because this condition is true for every element X belonging to the vector space X, and also ej, these are forming the basis of X, so these are the elements of X. So in particular, we can take X is equal to ej. So the previous equation becomes summation beta k fk of ej is equal to 0. Now by definition, fk of ej that is del kj, and by definition del kj, if the suffix k and j are same, the value is 1, otherwise 0. So this equation implies that beta j is equal to 0. Now we have proved all the scalars in the linear combination summation beta k fk are 0. So this proves that the set F is linearly independent set. Now next we prove that every element F of the dual space of X can be written as a linear combination of elements of F in a unique way. So let us take an element F belonging to dual of X. Now because e1, e2, e3 up to en, these vectors forms the basis of vector space X. So by definition of basis, every element of X can be written as a linear combination of these vectors. So for every X belonging to X, we have the representation of the form summation exile j ej, where j varies from 1 to n. Therefore from here f of X will be f of summation exile j ej. Now this can further be written as summation f of exile j ej. This can further be written as summation exile j f of ej. Now let us take f of ej is equal to alpha j. So f of x becomes summation exile j alpha j, where j varies from 1 to n. Now fk of x, substituting the value of x here, the value of x is summation exile j ej. So this becomes fk of summation exile j ej. Now this can further be written as summation exile j fk of ej. Now fk of ej, that is del kj, and by definition of del kj, when k and j are same, the value is 1, and when k and j are different, the value of this function, that is 0. So fk of x, that becomes exile k. Now we can substitute the value here. So we get f of x is equal to summation, the value of exile j from here will be fjx. So this will become f of x is equal to summation fjx into alpha j. It means this is further is equal to summation alpha j fj of x. So we have proved that f can be written as a linear combination summation alpha j ej, and this proves that f is a basis of x star, and because this basis consists of n vectors, so the dimension of the dual of x, that is also n, and also the dimension of vector space x is n. So we can say that the dimension of algebraic dual of x is same as dimension of vector space x. So this completes the proof of the theorem. Now next we do the lemma, which is called zero vector lemma. So according to this lemma, for a finite dimensional vector space having the dimension n, if x naught is a vector belonging to this vector space is such that f of x naught is 0 for every f belonging to the dual space of x, then that element x naught is also 0. So we have to prove that f of x naught is equal to 0 implies that x naught is also 0. Now because x is finite dimensional vector space, so we can take its basis. So let us take the set consisting of the vectors e1, e2, e3 up to en, that is the basis for the vector space x. And now because this is basis and x naught is a vector of x, so by definition every element of x can be written as the linear combination formed by these vectors. So let us take the scalars exile 01, exile 02 and so on up to exile 0n, such that x naught can be written as summation exile 0j ej, where j varies from 1 to n. Now let us find f of x naught. So applying f here, this will become f of summation exile 0j ej. Now this can further be written as summation exile 0j f of ej. Now let us take f of ej or alpha j. So we get f of x naught is equal to summation exile 0j alpha j, where j varies from 1 to n. Now we are given that f of x naught is 0 for every f belonging to the dual space of x, and from here f of x naught is this value. So we can say that summation exile 0j alpha j is equal to 0. For every choice of scalars alpha 1, alpha 2, alpha 3 up to alpha n, we have exile 0j is equal to 0 for every j varying from 1 to n. So this proves that x naught is equal to 0. Thus we have proved that in a finite dimensional vector space x having the dimension n, f of x naught is equal to 0 implies that x naught is equal to 0. This lemma is called zero vector lemma. and we use this lemma in order to prove the algebraic reflexivity of a finite dimensional vector space. So our next theorem is a finite dimensional vector space is algebraically reflexive. So let us take X is finite dimensional vector space. We proved that X is algebraically reflexive. In order to prove X is algebraically reflexive, we have to prove that the range of the canonical mapping C, which we discussed yesterday, the range of the canonical mapping C is same as X double star. X double star, that is the second dual of the vector space X. In order to prove these two vector spaces are equal, we have to prove that the dimension of range of C is same as the dimension of X double star. And in order to prove this, we are just to prove that dimension of vector space X is same as the dimension of its second dual. So firstly, let us define the canonical mappings. For this, let us take an element X belonging to the vector space X be fixed, and we define G of F is equal to Gx of F is equal to F of X, where F belongs to the dual space of X. This function G, that is a linear functional. In order to prove this is linear, let us take two scalars alpha and beta and two functionals f1 and f2 belonging to the dual space of X. Now let us find the image of alpha f1 plus beta f2 under this functional Gx. By definition of this functional, Gx of f is f of X. So this will become alpha f1 plus beta f2 of X. Now this can further be written as alpha f1 of X plus beta f2 of X. Now because alpha f1 and beta f2 are the members of X star, so they are linear. So this can further be written as alpha f1x plus beta f2x. Now f1x is gx f1 and f2x is gx f2. So we get the image of alpha f1 plus beta f2 under the functional gx is equal to alpha into gx f1 plus beta into gx f2. So this proves that this functional is linear functional, and therefore by definition this functional that belongs to X double star. Hence to each X belonging to the vector space X, there corresponds a functional Gx belonging to X double star. So we can define a canonical mapping C from X into X double star given by C of X is equal to Gx. This mapping is a linear mapping, and now we prove that this mapping is 1-1 mapping. To prove the mapping is 1-1, let us take an element X belonging to the vector space X such that the image of this element under C is 0. Now we prove that this element is also 0. Now because C of X is 0, so by definition of canonical mapping C, it means Gx is equal to 0. Now Gx is 0 mapping, it means under this function image of every element of X star that will be 0. Now the elements of X star are functionals, so we can say that Gx of f is equal to 0. It means f of X is equal to 0 for every f belonging to X star. Now because X is finite dimensional vector space and X naught is such that f of X naught is equal to 0, then we can use zero vector lemma. According to that lemma, f of X naught is equal to 0 implies X naught is 0. So using this lemma here, because here f of X is 0 and the vector space X is finite dimensional, so using this lemma we have X is equal to 0. Thus Cx is equal to 0 implies X is equal to 0. So this proves that the mapping C is 1-1, and therefore we can say that this mapping is invertible mapping. So we can define its inverse from range of C into the vector space X. Now because X is finite dimensional, and therefore the dimension of range of C is same as dimension of X. Now also we discussed in the previous theorem that dimension of X is same as the dimension of its algebraic dual X star. Similarly, the dimension of X star is equal to the dimension of its dual. The dual of X star is X double star. So from here we have obtained dimension of vector space X is same as the dimension of X double star. Now because range of C that is contained in X double star and the dimension of both two are same, so we can say that the range of C is same as X double star. So we can say that X is algebraically reflexive. So this proves that every finite dimensional vector space is algebraically reflexive.